Hello, my name is Yaroslava Lochman. I will present the work minimal solvers for single-view lens-distorted camera auto-calibration. We propose several minimal solvers that use combinations of image translational symmetries and parallel scene lines to rectify image scene planes and auto-calibrate cameras. The input to the method is a single image that can be lens-distorted. Given that the scene contains orthogonal lines or translational symmetries, the method auto-calibrates the camera. The calibration is used to rectify the three mutually orthogonal planes in the scene. These three planes define a coordinate system called the Manhattan frame, which is used to place constraints on calibration parameters. For the case where all lines and symmetries are coplanar, we propose solvers that can affinely rectify the image scene planes. Auto-calibration from a lens-distorted image is ill-posed. Good feature coverage across the image is necessary for good results. Translational symmetries and parallel scene lines are common in urban scenes, and each can be used to rectify planes and auto-calibrate cameras. Parts of the scene may be covered by only repetitive texture or only edges. Using both can provide better feature coverage across an image. Accurate measurements of imaged parallel scene lines are provided by circular arcs that are fitted to linked edges. Local feature detections give the measurements of image translational symmetries. State-of-the-art solvers can rectify or auto-calibrate lens-distorted images with either circular arcs or translational symmetries. Circular arcs provide accurate measurements, but it is hard to group them into sets of imaged parallel lines. Local features are easily grouped by appearance into translational symmetries, but they are noisier than arcs. We propose solvers that combine the best properties of both feature types. We also propose new arc-based solvers that solve for scene configurations that are not handled by the state-of-the-art. The proposed solvers use the invariant that the imaged parallel lines intersect at the vanishing point of their translation direction. The parametric form of the imaged scene line depends on whether translated symmetries or circular arcs are used. Solver generation follows the same steps once the vanishing points are constructed. We can easily generate solvers using either all points, combinations of points and arcs, or all arcs. We don't know the configuration of the vanishing points in the scene beforehand. Suppose that the three undistorted vanishing points are coplanar. Then they are incident with the scene plane's vanishing line. This constraint is used by the rectifying solvers. Also, the arc-based solver 5CS star imposes the constraint that the two of the vanishing points are coincident. The solvers return the undistortion parameter and the vanishing line. The number of solutions of the undistortion parameter returned by each solver is reported next to the solver names. The C++ optimized implementations of the solvers have mean time to solution of around 1 microsecond. The solvers have a simple algebraic structure, thus are fast and suitable for model selection in RANSAC. Now suppose that the three deducted vanishing points are the images of a Manhattan frame. The solvers use the constraint that the back-projected vanishing points are mutually orthogonal. In this case, the solvers recover lens undistortion, focal length, and absolute orientation of the camera with respect to the Manhattan frame. The feature combinations for the orthogonal configuration are the same as for the coplanar configuration. The warp error is a geometric measure of focal length and lens undistortion accuracy. The image is uniformly tessellated by a grid of points, which are back-projected by the gold standard intrinsics and reprojected by the estimated intrinsics. The root mean square distance of the grid and its reprojection is reported. The plot on the right shows the change in the warp error due to perturbing each calibration parameter independently. The solvers are evaluated on the standard AAT dataset that has 102 barrel distorted images. Statistics are accumulated over 10 evaluations since RANSAC is used. The proposed solvers outperform the state-of-the-art on 88% of the dataset. We show some examples where a particular solver performs better than the others. The box plots show the summary statistics for each solver over 10 runs. The previous examples and the top 1 solutions result show that the solvers are complementary. We use the AAT dataset to compare standard RANSAC that invokes a particular solver with the modified RANSAC that samples from a valid combination of arcs and local feature correspondences and invokes the solver that matches the sample depth. We test all solvers in combinations and a combination of the proposed 6CA and hybrid 2PC plus 4CA solver. We obtain the best results from combination of the proposed circular arc 6CA and hybrid 2PC plus 4CA solver. We also observe that the RANSAC estimators that use combinations of solvers perform better than standard RANSAC. Thank you for your time. Please see our preprint for details and the code release on GitHub.